So we'll be looking at Anova. You might have been hearing of Anova. Anova is analysis of variance, just an acronym for analysis of variance. So you're going to see the reason for using Anova. We use Anova to compare means of more than two groups. You know, our last discussion was on t-test. And what we use t-test to do is to compare means of two groups or compare two means. We may not say two groups because we have one sample t-test, pair sample t-test, and independent sample t-test. Whichever way you are comparing means, two means. But in a situation when you have more than two, like when you have three groups, for example, now maybe you have some people that maybe you want to check their weight. Some, they prescribe exercise for them. Some, they prescribe diet for weight loss. We have third one, which is control. So if you have two groups of people, you measure their weight, you want to compare, you have three means. Mean for group A, B, C. You want to compare. So we don't use t-test to do that. We'll go to explain the reason why we don't use t-test, and we now use what is called analysis of variance. You remember the logic behind hypothesis test was well explained by using mean and by using t-test, because the simplest, as I said. So you remember formula for independent t-test, for dependent t-test, one sample and independent t-test. Then in a situation where you want to compare three means, imagine somebody, maybe three or four, maybe anything more than three groups or more than two groups. Imagine somebody wrote a formula for you like this. Say this is F, this formula for Anova. It's look cumbersome. Sigma x bar minus double s bar square over j minus 1, everything over sigma x minus s double s bar square over sigma n minus 1. You're disturbing the class. So, but don't be discouraged. I just put this one forward because this is what the formula for Anova we are talking about. But it's not the formula. You can actually understand the concept without climbing the formula. But by the time you understand the concept, you discover that it's very simple. As it is very, very simple. And that is what we want to do now. So comparing more than two means, we use Anova, which means analysis of variance. It's a group of statistical methods employed to compare the means of three or more groups. It is good to understand that the t-tests are not used to compare means of more than two groups, as I've said. Therefore, the reason is it's good to have an understanding of the concept of family-wise error rate. It's because of that family-wise error rate. That's why you cannot use T to t-test. You know, t-test, it's compared two groups. So if you have three groups now, you have A, B, C. You have three means, A, B, C. If you have to use t-test, you have to pair them. You pair them, and how many ways can you pair? Three things. You can pair them, pair me to arrange them 2 by 2. If you remember combination. If you apply this formula, you see is combination NR. That is, in any way can you arrange n number of things in a R number of way. For example, now, n is 3 groups. R is 2 because we want to pair. Imagine how many ways will you pair? So this just, you don't need to cram this, just for you to explain the concept. So C is the number of possible combination of the two groups. N is number of items. Unit of combination is R. If we say we want to pair, let's say we want to pair, how many ways can you pair 3 things? So the N is 3, R is 2, because pair means you want to arrange the 2, 2. So if you have, if you can, you remember this formula, similar thing came when we talk about binomial distribution. When we say n factorial all over n minus r factorial, you know what it means. So whichever way, you know that if you want to reject null hypothesis, normally we have to, at the beginning of your study, you set your p-value. I mean, your type 1 error rate at 0.05, which is 5%. Now, if you now want to, let's say you want to carry out about 3 tests now, 3 tests. You know, if you now, that's okay, the formula-wise error will be 1 minus 0.95. You know, when you say 0.05, the remaining, when you remove 0.05 from 1, it gives you 0.95. So 1 minus 0.95 will give you the error rate, which is 0.5. So if you carry out test 3 times, the error rate will be 1 minus 0.95 raised to power the number of times. When you do that, for different, for example now, the first row is 2 number of group. If there are, that's what we do in t-test. So the p-value, your error rate is 0.05. The second row, just forget about all those other things. The second row, 3, you carry out 3 pairs of tests. Your error rate will be 40.3%, which is 0.1. Can you see it has moved from 0.05 to 0.145 and 143 rather, which is 40.3%. If you carry out 4 tests, your error rate will be 26.5%. Instead of 5%, if you continue like that, if you carry out up to about 10 tests, your error rate should be 90.1. Can you imagine? So these 3, for example, now, if you have 3 groups, you can pair it 3 times, 3 ways. It's very simple. Here you have A, B, C. A and B, that's 1. A and C, that's the second one. B and C, that's the third way you can pair. Can you see now? So if you have 3 groups, now you want to carry out 3 t-tests. You know, in that case, you have to pair them 2, 2, 2. If you have to carry out 3 tests, t-tests for 3 groups, you're going to carry out 3 t-tests. If there are 4 groups, it's going to be 6. You look at it now. A, B, C, D. We have 4 groups, A, B, C, D. A and B, pair 1. A and C, pair. A and D, pair. B and C, you pair, that's 4. B and D, you pair, that's 10. C and D, making 6. Can you see now? If there are 4 groups of mean, you want to carry out t-test, you have to pair them 6 times. If there are 5, you have to pair them 5 times. If there are 6 groups, 15 times. Can you see? 7 groups, 21 times. 8 groups, 28 times. And that's what gives you this error rate. So, and the layman way of understanding it is that if you have to carry out, the more the test you carry out, the more likely one will be significant. Even naturally, there's nothing that should be significant there. For example, I just as somebody that doesn't, maybe he doesn't have, is not intelligent enough to pass exam, or to even that he doesn't even understand, maybe to be in that level, he's not intelligent, doesn't know enough. And if the person continue writing the exam over and over, there's a probability that he will just pass one time. Pass one time does not mean that he's better. He has just passed the exam. If you see that he has not improved, it's only that he has been doing the exam, just gambling, just pass. It's the same thing. So if you have to carry out too many tests, there's a probability that at least one will be significant. even when there's nothing there. That's just a summary. So, in order to overcome the the intelligent people came with the idea that, look, it doesn't make sense. What we can do when we have more than two groups, when we have to carry, instead of carrying out many t-tests, it's good to carry out a test that first of all screen to see among this group, is there any different anywhere? And that test is the Anova, analysis of it. So instead of using the mean directly, they use the variances. Though actually, even it's the same logic anyway. Even the mean, in t-test where we compare the mean, we use both the mean and the variances. If you look at the formula, you see the mean there, you see the standard deviations there, which is square root of the variance. So I've already told you standard deviation and variance is just the same thing in a different way. It's like water and ice block. Ice block is water. If you want it as liquid, you melt it. The same thing, water is ice block. If you want it as a block, you go and freeze it. So it's the same thing, variance and standard deviation. So even in the comparing means in t-test, you still make use of, but here, because it's a robust arrangement of variance, that's why they call it analysis of variance. So analysis of variance, also called F-test. But that's not the only thing you use it well. You use the F-test for many things. Well, even the other thing you mean is still analysis of variance anyway, comparing variances. So it tells us whether three or more means are the same or not. It produces F statistic, which is similar to the T statistic in that it compares the amount of systematic variance in the data to the amount of unsystematic variance. What I just mean that I've already told you, even in the ordinary mean, comparing mean, the numerator is the systematic you are looking at. Is there any difference between the group? The denominator is the inherent variability, which is measured by the standard error. So the numerator is the signal, the denominator is the noise. We want to be sure that the signal is far higher than the noise. It's the same thing analysis of variance is doing, but just in a very intuitive and robust way. So F is the ratio of model to error. You get to understand this anyway, model to error. It is called F-test to reflect the name of a person that developed the technique. That's Fisher, Sir Ronald Fisher. That's the man. Was a genetist. He's maybe probably the most cleverest person, rather. Now, theory of Anova. Let's look at. So Anova examined the variation across all groups at once using the concept of variation between group and variation within group. We'll talk about that later. If there's no difference between the groups, then the ratio of the variance between the group and within group should be one, since the variation will be the same. You know, I've already told you, statistical test is about division of one thing with the other. So we want to divide variance between the groups, divided by variance within group. If variance between group, which is numerator, is the same thing as variance within group, there won't be any association now because it will be one. So for us to see any difference, because what we are interested in, we want to know that the variance between groups, what you are variation between groups, is what you actually, which is the systematic variance you are looking at. You expect if actually there is a difference in the group, the variation between groups should far be higher than the one within, so that when you divide it, it will give you value greater than 1. Not only greater than 1, it should reach a critical value that is very far greater than 1. Variation between group divided by the variation within group, if it's equal to 1, means that there is no association. If the group means are different, then the variation between group divided by the variation within group should be greater than 1. So otherwise, unless if the other one is higher, it should be less than 1. So ANOVA is an omnibus test. The meaning of omnibus is that it's an overall test. It's testing if there's any difference among all the groups, anywhere. You know, when you have group three groups now, A, B, C, is there difference maybe between A and B? There's no difference between A and C, and there's no difference between B and C. There may be difference between B and C, no difference between A and C and B and C. You may have between B and C or A and C, and no difference between A and B and whatever, or B and C. So you may have different between all the 3 combinations. So what ANOVA is testing is omnibus, mean just is there any different anywhere? It will not tell you where the difference lies. It doesn't provide information about where the difference lies. So if you get to know there's a difference somewhere, it's something else we do. We now move further. So it's just more like a screening. If there's no difference, by the time you do ANOVA, there's no difference. You leave your rest case, there's no difference anywhere. But if there's difference, you have to go further to do something else, which we'll talk about later. So that's what I just put is what I've explained. However, there are several ways in which mean can differ. All the 3 mean may be different. Mean 1 by x1 is not equal to by x2 is not equal to by x3. But you may have by x1 and 2 the same, but not equal to by x3. You may have by s2 and 3 the same, but not equal to by s1. You may have by s1 and 3 the same, but not equal to by s2. So let's use an example to us understand all these jargons, because without example, you will not understand. All the use robust, all those variations within, you're going to get to see them now with your eye. So this is an example of libido score of 3 groups of participants with different interventions. So this group, we have 5-5. There are 3 groups of people. These 3 groups of people, they are 15 in number, divided to 5-5-5. You told all of them are 15, but we divided to 5-5-5. So they were given different doses of Viagra, sildenafil citrate. For you that are not medical people or health people, Viagra is a drug to increase libido. So they were given to these people, and after they are given, they asked them to go and do what they know how to do and report score verbally on a scale of 1 to 10 to really know how is their libido. If you are to rate your libido between scale of 1 to 10, which score will you give? So how they rate is not your problem. Leave that one. It's the data as a statistician. What happened before is not your problem. What your own headache now, how to analyze the result. So let's say they have given the result now. And there are 3 groups. So group 1, placebo. Group 1 is a control. In the placebo mean there's no drug given. They give something like shock. When they give you shock as per something like just like tablet, but there's no active ingredient. It's called a placebo. It's like you are taking nothing. That's the control. Group 2, low dose Viagra. Low dose. Maybe they give 1 tablet. Maybe low dose maybe mean 1 tablet for that person. Then group 3, high dose may mean 2 tablets. So you can have 3 groups now. Group 1, nothing given, solely control. Group 2, low dose. Group 3, high dose. And these are the score. You see there are 5 score under each. And if you had all the score under group 1, you see that you divide by 5, it gives you 2.2, that's the mean by X. And if you calculate the standard deviation of 1.3, the variance is 1.7, the variance is just square of standard deviation. After all, it's variance you even calculate before you calculate standard deviation. If the variance is 1.7, square root of 1.7 is 1.3. If you square 1.3, it gives you 1.7. So group 2, 5 of them, if you had together divide by 5, it gives you 3.2. Mean is 3.2. The standard deviation is 1.3. the variance 1.7 also. Group 3, you add everything together, you calculate the mean, give you 5. The mean is 5, the standard deviation is 1.58, and variance 2.5. Then you can, that is for each of the group. You can actually collapse all of them as 15 of them and add everything together and divide by 15. You got the grand mean, total overall mean, which is the grand mean. That's why you have 3.467. And the standard deviation overall is 1.767 and variance to 3.124. Now, you will see what we mean by analysis of variance now. There are three variances, level of variability, variances. So when we talk about variance here now, just picture either variance or standard deviation. It just measure variability, any of them service. So actually, variance is the answer, is the real thing. But while we talk about standard deviation, that you remember when we were discussing how you calculate all these variance from mean. When you calculate mean, you now remove mean from each value. You have square deviation from the mean. When you square the deviation from the mean, because if you are to add all the deviation from the mean, it will give you 0. Some will be negative, some will be positive, because mean is in the center. So if mean is in the center, when you are removing each value, original value from the mean, you are removing mean from original value rather. Those ones that are smaller than the mean will give you negative value when you remove mean, which is bigger from them. The ones that are greater than the mean, when you remove mean, give you positive. The ones that are equal to the mean, it give you 0. So you go to have, if you try to add them together, as much that are negative will be positive. When you add it together, it give you 0. So variance, the deviation from the mean, the sum is usually 0. That's why it's useless. That's why intelligent people can only make sense from the data by squaring. That's where square come in. When you square x minus s bar, that is deviation from the mean, it gives you square. So, and that is how you calculated variance. When you add all the square together, square deviation, you divide by the standard, by the degree of freedom, n minus 1, it gives you variance. The variance is actually related, but you cannot quote mean and add v. You cannot say mean plus or minus variance, because the square has introduced square of the unit. If let's say the mean is measured in kilogram weight now, so the variance will be kilogram square, because there's a square there. That's why to revert back to the original value, you now calculate the square root of variance, which is the standard deviation. That's the logic behind calculating standard deviation from the variance, because you'll be able to quote, oh, mean plus or minus this, because mean and the standard deviation have the same unit. But otherwise, when we talk about variability here, we talk much of variance. Variance, how different are they? Now, there are 3 levels of variances here. One, if you remember, and there's something I did not say. You know, I first told you for each of the unit, you calculate the mean, you can see the variances calculated now. That's one level. For each of the group, you can calculate the mean, the standard deviation, the variance. That's one level of variance. That's variance within each of the group, variance within each. Now, I told you that you can collapse all the 15 together and now calculate the mean and standard deviation and variance. That's the total variance because you didn't divide them into groups. You collapse it. That's the total variance you can get in the data set. That's the overall variance, total. There's variance between. You know, another way of calculating the grand mean, instead of adding everything together and divide by 15, you can actually add the mean of each group together and divide by 3. You add 2.2 plus 3.2 plus 5 and divide by 3, it still give you the mean, grand mean. And you can still have the variance of each group mean from the grand mean. That is this variance between. That's the third level of variance. variance between. So we have variance within each group, variance between the groups, and overall variance. And you're going to see that the variance between within each group and between each group add up to give you the overall variance. Let's look at the demonstration on this slide. So this slide you see now, when I was giving this workshop on statistics in Port Harcourt one of these years, and I was explaining Anova, I was struggling because people didn't understand. So that day, and that was the last topic I treated for that day. When I reverted to my hotel room, I began cracking my head. How will I explain this thing? It just came to my mind, and I generated this with Excel. I generated this. It's the same data set. I generated it with Excel just to explain. And from the following day, I just gave it to them. People just understood. And from that time, I don't even bother myself. That's why I use the best way to explain this. Now, look at this table. Look at the first column. The first column is serial number 1 to 15. It just shows you the 15 people that participated in this video study. Now, the next column is group. Which group do they belong? You just list them. 1 to 5 is group 1. That's the first group. Number 6 to 10 is group 2. Can you see? Number 11 to 15 is group 3. The third column, X, is the value of each of the individuals. You just arrange according to each person. Then the fourth column is now where when we have calculated mean for each group. 2.2 for group 1, 3.2 for group 2, 5 for group 3, then overall mean, which is 3.47, which can be calculated either by collapsing all and divided by 15 or by adding the 3 mean or divided by 3. Can you see? Now, that fourth column, n minus x bar, what it does is to remove the mean of each group from each value in each group. Forget that we arrange them serially. So what they do now is from number 1 to 5 now, we have removed 2.2 from each value to give you what you have in that column, x minus x bar. So from serial number 6 to 10, their group mean is 3.2. We have removed 3.2 from each value, x, to give you what you have there. From number 11 to 15, the mean for the group is 5. We have removed 5 from each value to give us what we have. You're going to see negative, positive. If you add them together, it gives you 0. So it's not useful. I already told you that. You now square it. When you square x minus x bar, it gives you x minus x bar square, which is the fifth column. X minus x bar square. So, of course, when you square it, it removes that negativity from it. So you can now sum everything together. The sum is 23.6. This is what we call sum of square. So, this is not new because when we're doing ordinary mean and variance, it's the same thing. X minus x bar, they will now square it, the variance in the deviation. We now sum it together. That is sum of square. If the sum of square, we divide by n minus 1, which is degree of freedom, that give you variance. So it's the same thing here. So this is sum of square. This sum of square for this data is 223.6. So very soon, when you run Anova, you run regression, you'll be hearing sum of square. Later, I will explain to you that regression and Anova is the same. They are two faces of the same coin. I will explain to you. In those days, the researchers that were interested in experimental research, they use Anova a lot because they will divide the group into many groups, 3, 4, 5, 6, even as many as they can, because they were trying to control for confounder at the inception, at the design stage. So we tend to have many groups, small sample, but many groups. But the researchers that were doing observational study, because they could not control for confounder at the inception, because it's difficult to do experimental research in real life because of ethical issues. So you just need to study, you just need to go with what you can do. So the confounders are there. It is during analysis that the observational researcher, they now run analysis to remove confounder and they use regression. But they didn't know that they were actually doing the same thing. So you talk about that later. I will demonstrate to you that Anova and regression are the same. So look at this column 5, the sum of square. Now, this is sum of square within group. You know, because it's the variation in each, we calculate it for each of the group, even though we sum everything together. We sum everything together for the 3 group, but we calculate for each group separately, as you know. So it's sum of square within group. Now, the column number 6, which is fourth to the last column now. So you see by x, which is the mean of each group, minus by x, double bar. That double bar means grand mean. When you see double bar, grand mean. That is the mean, grand, which is 3.47. So this one I want to look at. No, we have already told you that you can add all the 3 means together and divide by 3 to give you the grand mean. You can even calculate the deviation, variance of each group mean from the grand mean. That's the second level of variance we are looking at, which is variance between group. The one we just explained is variance within group. But this one is variance between groups. So by x minus double by x, that is the group mean minus grand mean. That's what it means. You look at their deviation. If you look at it very well now, look at from number 1 to 5. They are the same number, minus 1.27. The reason being that the grand mean is 3.47. The group mean from number 1, group 1 is 2.2. When you say 2.2 minus 3.47, it will give you minus 1.27. Because it's the same mean for each, because all of them belong, number 1 to 5 belong to the same group. That's why it's the same thing. If you look at the number 6 to 7, which is 6 to 10 rather, which is group 2, you see the group mean is 3.2, the grand mean is 3.47. 3.2 minus 3.47, it gives you minus 0.27 for the 5 of them. While the last one, the number 11 to 15, you know, the group 3, the mean for group 3 is 5. The grand mean is 3.47. So 5 minus 3.47 give you 1.53, because that one is higher than the grand mean. That's why it's positive for all of them. Can you see now? Of course, if you try to add them together, it will give you 0. So when you square it, third to the last column now, when you square that one, it gives you, that is by x minus double by s squared. You remove the negativity. That is sum of square between. So you now add it together, it gives you 20.1335. So you have the first one, sum of square within is 23.6. This is sum of square between, 20.1335. So the sum of square within tell you the variability within each group. The sum of square between tell you the variability between the 3 groups. Between. Now, the second to the last column, what you now do now is look at the total x minus by s double by s. That is x minus the grand mean. Each value minus the grand mean, not the group mean now. Each value minus x minus the grand mean. So if you remove the grand mean, which is 3.47 from each value, it gives you this value. When you square it, it gives you the last column. When you add it together, it gives you the total sum of square, which is the total variability in the data set. If we look at the value now, the total sum of square is equal to the addition of the sum of square between, within, and the sum of square between. If you have 23.6 and 20.1335, it gives you 43.7335. Can you see?
Just
Now, Peter. So now, I think if you have question, you can ask me before we go further. You can ask. You can unmute and ask your question.
Question, sir.
Okay. Asuki.
How do we arrive at grand mean? I'm just coming in, sir.
You are a late comer.
Yes, sir. I agree, sir.
Dragging us down.
I'm sorry, sir.
So, anyway, for the benefit of some other latecomers, it's not only. So, grand mean, two ways you can get the grand mean. You can add all the 15 together and divide by 15, give you grand mean. You know there are 15 people, but they are divided into 3 groups, 5, 5, 5. The group mean was gotten by adding the value in each group and divide by 5. But the grand mean, by adding all the 15 and divide by 15, all the 15, but you collapse all of them and add together and divide by the 15. Or another way, you can add the 3 group mean together and divide by 3, whichever way. Is it clear now?
It's all right, sir.
Yeah. Any other one? Any other question? Okay. Now, you will see the logic behind the Anova, the F test you want to do, is looking at variance between group divided by variance within group. Variance between divided by variance. You know, variance between means that the variation between the 3 means, 3 groups, that's what you want to test. Is it actually a significant difference? Is it that because you already see the 2.2, 3.2, 5, they are different. But this difference is significant. You now, the variance between them, you want to divide it by the variance within each of the group. And what we have, 23.6, is sum of square within group. 20.1335, sum of square between group. How do you calculate variance from sum of square? You remember, you divide the sum of square by the degree of freedom, n minus 1. So for within group now, variance, you just divide 23.6 over 12. Because 12 is the degree of freedom. You know, each of them is 5. The degree of freedom for each of them is 5 minus 1. The sample size for each of them is 5. For each of the 3 now, n minus 1 is 5, making 4. 4 times 3, making 12. That's why the degree of freedom is 12. So 20.6 over 12, it gives you 1.967. That is the variance within. But that is why MS, mean square. You know, variance is mean square. That is average of the square deviation. Average. But the average is calculated not by divided by n, but by n minus 1, which is the degree of freedom. We already talked about that. Now, the mean square between, which is variance between, what you do is divide the 20.1335, which is sum of square between, over the degree of freedom, which is 2. You know, there are 3 groups. 3 groups, you represent as J. J minus 1, that is 3 minus 1. The degree of freedom for the between group is 2. So 20.1335 over 2, it gives you 10.067. F test is variance between, which is 10.067 over variance, which is mean square between 1.967. It gives you 5.119. If you go and check the table, this is F now. If you go and check statistical table, you have to check for degree of freedom, 2 degree of freedom now, between and within. Where both of them meet, that is where you see, okay, the degree of freedom 2 plus 3, what is the critical value? If you check now, the critical value is not up to 5.19. So it's actually significant. You know that you cannot calculate the p-value with hand. You only check the table, the table of this. But if you run with HSpaces or software, it gives you the p-value. So I run it, look at it, look at the setting. You know, this is HSpaces output. And see, look at Anova. You can see between group, square Look at what you calculate. Square, sum of square between group is 20.133. Within sum of square within group is 23.6. Then total sum of square 43.733. Exactly the same thing we calculate with that hand. And look at the degree of freedom for between group, which is 2, which is 3 group minus 1, making 2. The degree of freedom for within group is 12, which is for each group now 5 minus 1, making 4. In 3 places, 4 times 3, making 12. Total degree of freedom. If let's say you say all of them 15 minus 1 is 14. Can you see? N minus 1 overall degree of freedom total. You see, if you still add sum of square within and between, it will give you the total sum of square. If you add the degree of freedom between and within, it will give you total degree of freedom. Look at the mean square, which is the variance between mean and within, 10.067, then 1.96. Then F is division of this 10.067 by 1.967, give you 5.11. And the p-value is 0.025. Does it make sense? Does it make sense? Nobody answer me if it makes sense.
Yes, sir. Yes, sir.
It makes sense. Are you sure, Amina? It makes sense. Okay. Now, imagine, you know that formula I show you? Look at the formula I show you. So what we just did now is what I wrote. If you look at that formula I wrote with hand. Because it's difficult to type, to write it. That's why I have to write it and snap it. Sigma, if you look at it, F, we have just calculated now, is sum of square X bar minus gram X bar. Can you see? That, is between groups. First, X bar minus double X bar square over J minus 1, which is the 3 minus 1 we did here. The number of group. J is number of group minus 1. Everything over sigma X minus double S bar. That is sorry, it's not double S bar, it's single S bar. That's ordinary S bar. There is not double S bar over sigma N minus 1. Sigma N minus 1 means N minus 1 for each group. You have to add them together. There are 3 groups. So you see that the formula it looks difficult, but when you understand the concept. So normally, nobody will have, even if you are to even solve it, then we don't usually give it because it's prolonged something, but it's a simple thing for you to understand. It's just for you to understand the logic and get to understand. Is there any question before we move further? Any question? So now I want to quickly talk about F distribution now. Then when we now come back to when we have found the difference now, where does the difference lie? Because this F test, the Anova has not told us where the difference lies. How do you do that? We'll talk about it. But let me let's go through F distribution. It is distribution of all possible value of F statistic we just calculated now. Look at it. It depends on degree of freedom. And the degree of freedom, there are 2. So you know why I don't even talk about distribution until I explain this, because if I just talk about the distribution before I explain this example, you find it difficult because unlike other, there are here now, we talk about 2 different degrees of freedom for the same distribution. Whereas when we talk about chi-square, talk about t-test, it's just 1 degree of freedom for 1 distribution. But here, we have to have the degree of freedom between and within. And that's why if I talk about it now, just talk about F distribution, it will not make sense. But now that you understood that, you know the logic behind analysis of variance between, variance within, you know we have 2 degrees of freedom to consider. Even apart from overall, though the 2 degrees of freedom add up to give you the overall degree of freedom. So this is just like chi-square and T distribution. So the shape depends on the degree of freedom. And as the degree of freedom increases, the shape begins to look like normal distribution. Anything, we talk about central limit theorem. As the sample size increases, the degree of freedom increases, the shape begins to be like normal distribution. Look like that is begin to mirror normal distribution. So the curve is not symmetrical, but skewed to the right. That's how chi-square is skewed to the right. There's a different curve for each set of degree of freedoms. The F statistic is greater than or equal to 0. That is, it's like chi-square. It doesn't have negative side like normal distribution. And T and normal distribution, they have negative side. So the middle of that something is usually 0, while on the other side, negative, on the other side, positive. But for chi-square and F statistic, F distribution is from 0 to something else. No, there's nothing like less than 0. There's no minus value. As the degree of freedom for the numerator and for the denominator get larger, the curve approximates the normal. Now, numerator here means between groups. Denominator means within group. No. The S distribution is used in many cases for critical region for hypothesis tests and determining confidence interval. 2 common examples, Anova. So this F distribution is not only used for Anova. It's Anova. Then we also use for F tests to determine if variance of 2 populations are equal. If you remember, when we talk about normal distribution, when we talk about t-test, when we were talking about homogeneity of variance. When you run SPSS, I show you something. Though we didn't run SPSS. Anyway, I show you the output. It can give you output, when equal variance assumed. So in fact, we'll carry out what we call leaven test for equality of variance. If you want to test if 2 variances are the same, of course, it's by dividing them. If you divide them, it's 1. That shows that it's the same. So that's what leaven test does. So apart from Anova, though Anova also is comparing, is dividing 2 variances, but apart from that logic of between and within, but 2 variances, you divide them, want to see if they are the same. It's the same Anova, the same F test. But in that case, not Anova. You call it leaven test for equality of variance. So this is the statistical table, and you have numerator degree of freedom is along the horizontal, denominator degree of freedom along the vertical. So the horizontal one is the between group, vertical one is within group. For example, now the one we did, that's what we did. The degree of freedom for the vertical is 2. For the horizontal is 12. Remember, if you look at where 2 move, 2 join 12 is 3.89. And what we calculated is 5.119. Can you see? Because what we calculated now is above the critical value of 3.89. That was why it was significant. Of course, SPSS can give you the p-value straight. Does it make sense? So if I want to ask you to calculate, solve Anova now, I have to give you this statistical table in exam to check the critical value before you can make conclusion. Now, F ratio tests only whether the model fit to the model account for more than, okay. more than variation that is sinus follow, but does not factor, but does not tell us where the difference lie. What I'm saying is that when you calculate, you do your ANOVA F ratio, it just tell you, oh, there's a significant difference in the mean of these 3 groups or 4 groups or 5 groups. So there are differences. So there are differences somewhere. But where the difference lies, it doesn't know. Is the difference between, like for this one now, we have gotten different. Is it between A and B? Mean 1 and mean 2? Or between mean 1 and mean 3? Or between mean 2 and mean 3? We don't know. Because there are 3 combinations you can have. We don't know. There are 2 ways to contrast the different group without inflating type 1 error. That is, what you now do is, there are 2 ways you can now look for where difference. You compare them, not new, better. This comparison, you, without increasing the family-wise error that we talked about before in when we say that the reason for not using t-test, because you see pair them, some are pair, you say okay, A and B, but there's a way they will adjust in the calculation so that there won't be family-wise error. And 2 ways, we have plan contrast and post-hoc test. So this one, just explaining this one for you when we come out in the MCQ. Anyway, you're no more doing MCQ in your exam. In your final exam, we don't bring MCQ down. Just go and solve that day. But just for you to know, I will not bring out post-hoc test for you anyway to come and solve it, just for you to understand. So let me just quickly go to that post-hoc test. Forget about that plan contrast, because that plan contrast, if I try and be discussing that, it will blow your mind. So let's talk about post-hoc test. Yes, I think it's this slide. Yes, post-hoc test. These are the pairwise comparison that are designed to compare all different combinations of the group. Pairwise. When you say pairwise, it means that you are pairing. You are arranging them 2, 2. If you look at t-test, you run away from 2, 2 also. But in this one, you will pair them without inflating that type 1 error. China, we are. So they are used when you are interested in exploring that the data for any between differences between means that exist. Pairwise comparison control the family-wise error by correcting the level of significance for each test so that the overall type 1 error rate across all comparison remain at 0.05. So you don't want the thing to inflate more than 0.05. There's a way they tame it. There are several ways in which family-wise error can be controlled. The most popular and easiest way is to divide alpha by the number of comparisons to ensure that cumulative type error is below 0.05. So what it means that if you have, for this one, we carry, if you want to do, we have to pair them. If you pair this one, there are 3 groups, you're going to have 3 pairs. In that situation, they will not divide that p-value by 3 to slash it down so that that p-value to be divided by 3, half that level of significance, whatever, you divide, you slash it by 3 by the number of tests you are doing. This is a method called Bonferroni correction. But many people, there are many other methods. Many people criticize Bonferroni, including myself, because it's overcorrected. It tends to overcorrect. So there are other ways, even if you're not expected, up to about 18 that you can option we have there. I will just show you without solving it, because the formula for correcting them, they are rigorous. So nobody does that. But thank God for the, what do I call it, for machine, for software. You have already just to input it once and for all into the software, and it will run it for you. So those are the 18 different you can find if you use expenses. 18 different way to correct for that family one zero. It's very intuitive. I will explain. It's very simple. 18 different way. And if you look at this 18, 14 equal variance assume. If you, this number 1 to 14 now, you assume that for each of the group, they have the same variance. But it's not all the situation you have homogeneity of variance. So that is homogeneity of variance is assumed. Homogeneity of variance is one of the conditions for using parametric tests. The first one is normally distributed. Second one is homogeneity of variance. Third one is dependent. Third one is at least on intervals level. The last one is independent. Now, if equal variance, you cannot say equal variance, and at least there's no homogeneity of variance. You can have for any of the other four. For this donut, game, OS, now, we've run. Let's say I've run it with I run the analysis with yes, Bonferroni. Let's say we run it with Bonferroni. Look at the question. Look at the logic. Yeah. Look at the result. Let's say we run it with Bonferroni. The way you have 3 things you want to pair. So when computer is not human being, so you program it, and there's no way you can do some programming without redundancy, in the sense that there will be repetition. Look at it. What you just want to pair 3 things. So if you say the best thing is to first of all hold one of them, see, look at I mean one group compared with J, the other group. So when we say placebo group 1, you can pair with low dose, or placebo pair with high dose. The second, if you hold high dose in low dose, compare with placebo, compare with high dose. If you put high dose, you can play with placebo, compare with low dose. Whichever way, you see that there will be repetition, in the sense that it's 3 things, it end up doing 16, because there's no way you can. It's the same thing when you are running the correlation. When we get there, do correlation, I'm going to show you. Now, placebo low dose is the same thing as low dose placebo. You agree with me? If you say placebo versus low dose, it's the same thing as say low dose versus placebo. Placebo versus high dose is the same thing as say high dose versus placebo. Low dose versus high dose is the same thing as say high dose versus low dose. You are disturbing the class. So when you now look at the p-value, significant, third to the last column, in SPSS, it give you p-value as significant, SIG. So who can tell me where the different lies now? It's a lecture, so you can unmute and answer. Where does the different lies? Nobody. Nobody. Asuku, want to talk? Where does the different lies?
I think between placebo and high dose.
Yeah, that's great. Who answer? Who answer?
Me.
Oh, Ekere. Kokonen. That's good. You're right. Between placebo and high dose, because that's the p-value that is less than 0.05. If you look at it, that is though it's just a coincidence that if you look at when we did something is the Anova, the p-value is 0.025. It's just a coincidence that is like that, but that is the only one that is significant. If you look at it, you see that 0.025 appear in two places. It's the same thing. Placebo and high dose and high dose and placebo is the same thing. You will see placebo and low dose is 0.845. Low dose and placebo is 0.845. It's the same thing. It's just like A and B and C is the same. Then you will see low dose and high dose 0.196 and high dose and low dose 0.196. Can you see? So three things. He repeated them in each of them. Repeat each. That's why you have 6. It's like say A versus B and B versus A, it means the same thing. But because the way it has been programmed, you first of all A, B, C, you line it up against the others. So there will be redundancy. So there's something I want you to look at that's very intuitive also. Because I don't want to issue of confidence interval. We have explained when we did the t-test, we explained the way confidence interval. The same thing come out here, but actually it's very simple. It's not a big deal. But what I just want you to look at the third column, the mean difference. That mean difference. We say the first column is high, one group, compared with the other group, J, second column. Then I say third column, say I minus J. The difference between I and that J is their mean. That is the difference. Remember, placebo, the mean is 2.2 for the group. For the low dose is 3.2. When you remove 2.2 minus 3.2, it gives you -1. That is, you remove low dose from placebo. You remove 3.2 from 2.2. Look at where we have low dose and placebo now. The third line. You see, it gives you 1. It's the same thing. You remove 2.2 from 3.2, it gives you 1. So, because of the redundancy, you remove greater from the smaller one, give you minus. When you remove smaller from the greater one, give you plus. Look at this, the second line. Placebo, high dose. You remember the mean for placebo is 2.2. For high dose is 5. When you remove 5 from...
Dear customer, the number you have dialed is not reachable at the moment.
You are not serious, okay, Gwen? You are on your this thing, you are disturbing us. So if you remove 5 from 2.2, it gives you minus 2.8. And you see the difference between the 2.2 and 5, 2.8. But if you come to high dose placebo, where you say you remove that 2.2 from 5, it gives you 2.8. The same thing, fourth line. Low dose, high dose. When you remove high dose, the mean for low dose is 3.2. High dose is 5. Remove 5 from 3.2 to give you 1.8. But if you say high dose minus low dose, you remove 3.2 from 5, give 1.8. Can you see? Now the last one. So this one I just explained to you, we use Bonferroni. But there are different methods. We have LSD. LSD means least significant difference. We have different methods. So imagine we use Bonferroni, LSD, and that if you do number 1 and 2 of these equal variance assume. Number 1 is Bonferroni, second one is LSD. Then among the other one, number 3 of equal variance not assume, game OS. We use these 3. Can you see LSD, Bonferroni, games OS to correct? You will see something. Look at LSD. That one that was significant placebo and low dose is 0.008. It's far, far less than 0.025 that one gave. It's more significant. Look at the one from Benforoni, I put it there also. You see 0.025. For this one, 0.0. So that showed that they already said that Benforoni overcorrect. That showed that if sometimes, if it's not, it may not be significant, you may not even find significant with Benforoni, you may find with LSD. Look at between low dose and high dose. With Benforoni, urine is 0.196, but with LSD, 0.065, almost significant. Look at also Games Owen, the same thing, 0.035. So it's even less significant than Benforoni. Of course, this one say equal variance not assumed. So different method of correction, if care is not taken, the difference may be there, you may not be find it. You may not find it different because you overcorrect. So one of those days in Port Harcourt, there was one in our lecture, in our workshop, the one PhD student, when I was taking this in, I said, okay. You remember when she did her analysis and she didn't find the difference, the supervisor now said, don't use Benforoni, go and use LSD. When she used LSD, she was able to find the difference. So I will encourage you, if you want to make correction, use LSD because Benforoni may overcorrect, tend to overcorrect. So this one just to show some light. Is it even necessary? Any question? Leave this one till when I go to regression. When I get to regression, I will come and I will see it, I will demonstrate. When we do regression, I will let you know or demonstrate how regression and Anova are the same. Then I will show you this slide. I will explain it. Any question?
Yes, I have a question, please.
Okay, go on.
So would you advise us then, when we are running analysis, to use multiple methods for the Anova? For instance, applying both LSD and Benforoni to identify if the significance is true?
Well, the question, you can run it just for you to experience it yourself. From what we have just said now, LSD will give you, is the best that will give you the difference. When even if LSD cannot find it different, the other one will not give you different. Benforoni will not give you, other one will not give you. But if you run this one, I did it for academic purpose, so to demonstrate to people, to prove that the Benforoni tend to overcorrect. That's why I did for different for you to see and encourage, okay, for you to know that it's better you use LSD. So when you are doing your just use LSD. You don't need to be using, after all, even if you use different something, it's one you're going to choose. You cannot go and show all the results. You cannot go and tabulate and say in your result that this is for LSD. No, you will not do that. I just put this one just for teaching purpose. So I don't know if I've answered your question.
Yes, sir, you have. Thank you.
You're welcome. Any other one? Any other? Some people are cooking. That's why they don't have questions. Go on. Fana. But we cannot hear you. Fana, are you talking? Any other? Okay. If there's no, so I don't want to, I need to let you know I've already talked about it. I don't want to open new topic because it will be too much for you to burn the remaining time. After 5, that will be, I don't want to start new lecture Or I should go and start new lecture because we need to talk about measures of association. Captain.